Greetings and welcome to the continuing lectures on equations and inequalities in two variables. Lecture 3.2, Slope of a Line. Have you ever been on a road that warned you about either you're going uphill or you're going downhill? Most of the time they give it to you uphill. For example, maybe you see a sign and it says a 6% grade over 5 miles. What does that mean? So if we're going downhill, our little car is going forward. That means for every 100 feet we travel forward, we have descended by 6 feet. We can think of that as a decimal, and we can also think of descension as negative. So negative 0.06 equals, we can do that as a fraction, negative 6 over 100. Or over negative 3 over 50. So what did that number mean, the negative 3 over 50? What that means is that it's the ratio of the vertical change to the horizontal change. So we're going to put the vertical change on top, the horizontal change on the bottom. Vertical meaning the 6 feet, horizontal meaning the 100 feet. And when we reduce it, we can also think of it as we descend 3 feet for every 50 feet we drive. Why would that be important? Well, slope measures the steepness of a line, or the steepness of our travel. And the higher the grade, the higher the percent of the grade, the either more steep it is going down or more steep it is going up. It measures the steepness. The larger the number, the numerical value, the stronger the steepness. If our line rises when we read it from left to right, something that looks like that, then the slope is positive. When a line falls going from left to right, and it looks something like that, the slope is negative. Think of it as going uphill and downhill as we read left to right. Okay. So visually, a slope like this, I started higher on the left than I did on the right. It is a negative slope. If I have no change whatsoever in my slope, that is a zero slope. And if I start lower and then get to higher, that is a positive slope. Mathematically, how do we figure out the slope of a line? We're given an equation, and we're going to choose some values for x so we can find some values of y. We need 2 points. 2 points to figure out the slope of a line. Okay. I'm going to go ahead and try x as 2. When I plug in 2, y equals 2 times 2 minus 3. 2 times 2 is 4 minus 3, so therefore y is 1. There's 1 point for us. 2 comma 1. Let's plug in 4. 2 times 4 is 8. 8 minus 3 is 5, so y will be 5. If I plot this line, here's my 2, 1, here's my 4, 5, and I've drawn my line. What I can think about is the change, the vertical change over the horizontal change. So let's say my first point was 2, 1. I went over to the right 2, and then I went up 4. Therefore, my horizontal change was 2. My vertical change is 4. 4 over 2 can reduce down to 2. Mathematically, we can figure this out as well, but this was just using geometry to figure it out. Now the slope of the line, if we are given 2 points or we figure out 2 points, it's going to be the rise over the run. Or we can think of it as, if I have 2 points, it's y2, y of the second point minus y of the first point, all over x of the second point minus x of the first point. Now, the rise over the run is the geometric form. That's just looking at a picture and counting some spaces. But sometimes it's too cumbersome to draw out a graph. Therefore, we can use this algebraic form. And this algebraic form will always work if we're given 2 points. Algebraically, if we want to look at it on a graph, I have 2 points. P1, which is x1, y1, just 2 generic points, and P2 is x2, y2. That means the rise is going to be y2 minus y1. That will be the rise. And the run, the how much lefting and righting I'm doing, is going to be x2 minus x1. So we don't necessarily need to draw this whole entire graph. We can just use the algebraic equation. Let's do an example. Find the slope of a line that passes through -2, 3 and -5, 1. Now algebraically, I have my nice equation, my nice formula that I can use. Slope, which we'll call m, y2 minus y1 over x2 minus x1. For argument's sake, I'm going to say -2, -3 is our point 1, and -5, -1, or -5, 1 is our second point. So y2 is 1 minus y2, 1 is -3, all over x2, -5, minus x1, which is -2. 1 minus -3 is going to be 1 plus 3, which will be 4. And -5 minus -2 is really -5 plus 2, which is -3. Now we don't leave the negative in the denominator. Either we're going to give it to the numerator or we'll give it to the whole entire fraction. But it's a -4/3. Now, what if I didn't want to solve it that way? I wanted to solve it geometrically. So I draw out a big graph. I plot my 2 points, -5, 1, -2, -3. I draw my line. And then I figure out, well, I'm going to call this -2, -3 my x1. So I run over to the left, which is negative, and then -3, and then I run up 4. So it's still 4 over -3, but again, we don't write it with the negative in the denominator, so we're going to give it to the numerator or give it to the whole fraction. You might be asking, does it matter the order in our points? Well, if instead of having -3, -3 be -2, -3 be my first point, I'm going to have it be my second point. And -5, 1 will be my first point. So let's see, is there any difference? Well, same formula, m equals y2 minus y1 all over x2 minus x1. This time my y2 is -3, my y1 is 1, my x1, or my x2 is -2, and my x1 is -5. So plugging it in, -3 minus 1 is -4, and -2 minus a -5 is going to be a 3. So the only difference is immediately my negative landed in the numerator instead of the denominator. But ultimately it doesn't matter. The slope is exactly the same whether I have point 1 be point 1 or point 1 be point 2. Let's try another example. Let's find the slope of the line that contains the 2 points 3, -1, and 3, 4. Using my slope formula, m equals y2 minus y1 all over x2 minus x1. And before I continue, I will say I recommend anytime that you use a formula that you write it down. Anytime that you use it. Because the more times that you write it down, the easier it will be to recall the formula that you need at that moment. So always write it down. All right, y2 is 4, y1 is -1. x2 is 3, x1 is 3. So it's going to be y minus -1 all over 3 minus 3. y minus -1 is 4 plus 1, and 4 plus 1 is 5. 3 minus 3 is 0. 0 is in the denominator, therefore it's undefined. Maybe that didn't give us enough information that we need, but let's check it out geometrically. When I draw my 2 points, 3, -1, and 3, 4, and I connect it, it's a vertical line. It's an absolute straight up and down vertical line, no slope whatsoever. Right? Think of it like this. Before, I've had a line like that, or like that, negative or positive. And the steeper I get with my line, the larger my coefficient is, right? My slope. Well, eventually, I can only get so big. I can only get so straight up and down, so steep, before I kind of hit a wall. Here, literally have hit a wall. A wall is straight up and down. It should have no slope. Therefore, when we run across algebraically undefined, that will equal no slope, not zero slope. That's something totally different, but no slope whatsoever. Our wall is not leaning one way or the other. It is no slope. Let's change our mindsets just a little and start talking about slopes of parallel and perpendicular lines. Parallel lines are going to be lines that never cross. Perpendicular lines are lines that cross at a right angle. Those are perpendicular lines. Okay. So parallel lines, they're on the same plane. We got to think about that. It's in the same area, but they never intersect. They're called parallel. And then think about this. If these two lines never cross, that they are parallel, then the two lines that are parallel, if and only if they have the same slope. Remember, slope determines steepness, and the moment that a slope changes for one line, they will eventually intersect. So two lines are parallel if and only if they have the same slope. Now let me talk about that if and only if. When you talk about if and only if, that works in both directions. So I can switch this statement around and say two lines that have the same slope if and only if they are parallel. Okay? If and only ifs work in both directions. So now let's chit-chat, and what I'm going to say if they're parallel, a shortcut, is line 1 is parallel to line 2. Therefore, line 1 is parallel to line 2 if and only if their slopes are equal. Now, two non-vertical lines are perpendicular if and only if their product of their slopes is -1. Yes, I know, not so obvious, but if their product of their slopes is -1. So line 1 is perpendicular to line 2 if and only if slope 1 times slope 2 equals -1. Another way of looking at that is, let's say slope 1 is 2/3 and slope 2 is 2/3, then the lines are parallel. They have the same exact slope. If slope 1 is 2/3 and the slope line of line 2 is -3/2, then the lines are perpendicular. Take a slope, take its reciprocal, and then the opposite sign of whatever the original number was. That will mean that they're perpendicular. For example, slope 2. The parallel line is also slope 2, but the perpendicular line is the reciprocal, which is 1/2, and opposite sign negative. So line that has a slope of 2 has the perpendicular line slope of a negative 1/2. Many times we need to extrapolate data from a chart or a graph and then be able to manipulate it using our algebraic sense. So here we have a chart. On the, what would be the y-axis would be dollars, and on the x-axis are years. And this is telling me that in 1955 a gallon of gas was 29 cents, and in 2005 a gallon of gas is $2.93. So what if this was actually a straight line between those points? What would the slope be? So algebraically, we're going to use our 2 points, our first and last point. Our first point, 1995, 29 cents. Our last point, 2005, and $2.93. Using our slope formula, y2 minus y1 all over x2 minus x1, we're going to get 293 minus 29 cents all over 2005 minus 1955. When we get down to it, it's 0.0528. So what does that mean? On average, it is a change of $0.058 per year. Now, it's a little bit hard to see exactly what was going on. So let's change our dollars to cents. Let's convert dollars to cents. So I'm going to take the 0.0528, multiply it by 100 to convert to pennies. So our average change in a gallon of gas is 5.28 cents per year. Now that's just the average change of price over a 50-year period of time. Now, let's take another look. This time, let's take a 10-year range, 1995 to 2005. That's a 10-year difference. The price in 1995 on average was $1.10 a gallon, and in 2005, $2.93. We're going to do the same algebraic formula for slope, y2 minus y1 all over x2 minus x1. Plug in your values, and you're going to get $1.83 for 10 years. Do that division. It's $0.183 per year, or again multiply it by 100 and you get 18.3 cents per year over a 10-year period. Much steeper change in the last 10-year period than it was for the overall 50-year change. Now let's talk about slope and average speed. If you consider our distance equals rate of speed times time, and let's suppose a boat is traveling in constant speed, 15 miles per hour in still water. So there's no current here, the boat's just moving. Let's figure out how we can graphically represent this and then figure out the slope. At 0 time, we traveled 0 miles, so 15 times 0 is 0. At hour 1, 15 times 1 is 15. Hour 2, 15 times 2 is 30. Hour 3, 15 times 3 is 45. Hour 4, 15 times 4 is 60. Hour 5, 15 times 5 is 75. So if we were to graph this, hours to miles, we see it as a steady slope. And if we figured out that for every change, 1, the run is a 1, the rise is a 15. Run is 1, rise is 15, 15 over 1, that is a slope of 15, as to be expected because we're only changing it by 15 every single time. But we can take just two random points. We'll take 3,45 and 2,30. Plug it into our formula, 45 minus 30, all over 3 minus 1, 15 over 1. Average speed is 15 miles per hour. Let's look at another. Given a graph, let's figure out how fast a car is traveling at constant speed. At 2 hours, they traveled 120. At 4 hours, 240. 6 hours, 360. Now we can look at this between the first point and the second point. The change in x was 2. The change in y was 120. So rise over run, 120 miles over 2 hours, that's the constant speed of 60 miles per hour. So that's it for this lecture. Until next time, be seeing you.